Hello and welcome to Hadoop tutorials at Learning Journal. In the previous session, we learned about mapreduce programming technique and mapreduce execution engine. You may not be using mapreduce engine in your real-life projects. However, having a reasonable sense of mapreduce problem-solving approach is necessary to grow in big data space. The best way to understand this subject is to solve some problems using a mapreduce technique. Let me list down some simple problems, and we will try to address them using mapreduce method. So, we have 6 problems listed here. These are incredibly simple problems, but they are an excellent tool to enlighten your mind with mapreduce programming approach. I will explain the approach for solving these problems using a mapreduce technique. However, if you are interested in the code for these examples, it is available in my GitHub repository. Before we start building mapreduce solutions, let me quickly refresh few things. How the mapreduce framework executes your map function. The framework will run multiple instances of your map function on different computers in your cluster. The framework will also attach one input split with each map function instance. The default input split is equal to one block of data. The framework will call your map function in a loop and pass one record at a time from the split. The output of map function is a key value pair, and it goes back to mapreduce framework. These 4 points are the essential basics for a map function. How the framework executes your reduce function. The framework will collect output records from all map functions. Then it will do a shuffle sort and assemble all the map outputs into one record for each key. So, if you have written 3 different keys as output from your map function, you get 3 records. Each record is then passed to the reduce function one at a time in a loop. The output of reduce function is again a key value pair, and it is written to HDFS in a file. These 3 points are the basics of a reduce function. The most important part is to understand how a record is created after shuffle and sort. If you can visualize your record for the reducer, you can write a correct reduce function. Okay, before we start solving our example problems, let me quickly explain the process of compiling and packaging mapreduce programs. I am using SBT to compile and package my code. You can install and configure SBT using the link provided in the description. However, I have a video demonstration for the same in my Scala tutorial playlist. Once you have SBT, rest is simple. Create one directory and place your Java source code in the directory. SBT uses a build file named build.sbt. Let me show you my build file. So the first line is the name of my project. The second line is the version number of my project. The third line is the Scala compiler version that I want to use. The next line is critical. It represents the Hortonworks online repository. Most of the open source projects depend on several other projects and packages. Sometimes resolving those dependencies is a tough task. I often see beginners searching for dependency jar files. To simplify the process, most of the open source projects host the dependency jar file at some public repositories. Maven Central is one of the most commonly used and default repository for many build tools, including Apache Maven and SBT. However, some vendors maintain their own repositories outside the Maven Central. In those cases, we need to specify their repository URL as additional dependency resolver. Since we are using Hortonworks platform, I added their public repository URL as an additional dependency resolver. The next two lines are to define actual dependency. We need two things for our example: Hadoop Common and MapReduce Client Core. You might be wondering, how do I know which version is required? We need to find the version of our target cluster. We already learned it in an earlier video, but let me show you it once again. You see this version number? That's what I am using in my build file. I recommend that you check your cluster version and change the version number in your build file accordingly. Good. Now you can compile and package your MapReduce code into a jar file. SBT will create your jar in the directory named target. Okay, let's come back to our example. We have already seen line counting problem. Let's look at the next problem. Let's assume that you own a global video tutorial portal. You have a system in place to record some information about every video play session. You are recording a start and end timestamp and few other things like user ID, video ID and play mode, etc. Your data is available in HDFS as a CSV file. Now, you want to find average play time from this file. How will you do it using a map and a reduce function? It's very simple. We already know that the framework will call our map function in a loop and send one line from the CSV file in each iteration. Let's look at the one line from the CSV. What do we have? The fifth column is the start timestamp and the sixth column is the end timestamp. We will take these two fields from our line and ignore everything else. Then we will calculate a difference between these two timestamps in seconds. That's our playtime duration. Let's quickly look at the code. So, this is the code for the mapper. When we extend the mapper class, we specify 4 data types. The first two are input data types for the mapper. Since we are not using input key, we take it as object. The value is a text, and that's obvious because each line in the file is a plain text. The next two parameters are data types for map output. We have taken the key as a text and value as long writable. Choosing a right data type is critical, and we choose them based on our data file and the logic that we want to implement. We prefer long as an output type because we will pass playtime duration, and that's a number, right? Rest of the code is straightforward. We are splitting the line using a comma, taking the fourth and fifth fields, calculating the difference in seconds. Now we want to calculate average. To find an average, we need to collect all such playtimes at one place. We know that the framework will collect all the map outputs and pass it to the reducer. So we hand over the playtime to the framework. Since we want all such durations to be collected in a single record, so we pass a constant key for the map output. That's it. The map part is over. Let's come to the reduce part. We know that the framework will collect all map outputs. Let's assume you have these outputs from various map functions. Since we have just one key, so the engine will create only one row. It will collect all these values into an array and attach that array to the single record. That's it. The record for a reducer is ready. The framework will call the reducer and pass this row. Now, you can write a simple loop to sum these values and calculate average. Simple, isn't it? Let me quickly explain the main method as well. The first thing is to create a configuration object. The config object will read some configuration files from the default locations. These configuration files provide cluster details, and that is necessary to execute your program and read your input data file. The next thing is to create a job object and set some properties. We need to set 3 class names: the main class name, the mapper class name, and the reducer class name. Then we configure the output key data type and the output value data type. Finally, we set input and output directories and execute the job. Good. So we solved our first problem. Let's execute it and check the result. Now, let's look at the next problem. Average by a group. What does that mean? So, this time we want to calculate average view duration for each unique video. In fact, it's an extension of the earlier problem. We computed average playtime for all videos. Now we want to calculate the average for each unique video ID. How will you do it? Let's look at the map function first. Everything remains same because we still want to read both the timestamps and calculate the difference. Now we want to calculate the average for each unique video ID. The trick is simple. Instead of putting a constant key, we use video ID as a key. I'm sure you already guessed the effect of using video ID as a key. In our sample data file, we have data for 2 unique video IDs. So this time the framework will see 2 unique keys and hence it will create 2 records for the reducer. 1 record for each video ID. It will collect all the values for the first video ID into one array and attach it to the first row. Similarly, it will gather all values for the second video ID and attach it to the second record. Both the rows are ready. Now the framework will call the reduce function and pass these 2 records. There is one more important point to note here. The framework will also sort the records by key. That means the video ID 57 comes before video ID 65. As a result of sorting, the output is always sorted by key. The sorting is one of the key design features of the mapreduce framework. We don't need to change anything in our reduce function. The same reduce function is valid in this example as well. Let's execute it and check if everything works as expected. Good. So we solved 2 problems. Counting words in a large file is a famous example, and you can find the source code in Hadoop documentation. So I am not going to cover that. We are still left with 2 more examples. I will cover them in next video, and I will also talk about MapReduce logs in next session. Thank you very much for watching Learning Journal. Keep learning and keep growing.